we're using the Celsius scale. It's kind of warm above the freezing point of water. Those are positive numbers. Water freezes at 0 degrees Celsius. What if it gets even colder? Which I don't usually experience here in Arizona. But look at here. This is negative 10 degrees Celsius. That's cold. So it is important to have negative numbers, for example, with temperature. The lower it gets, the colder it is, so the more negative the number. Rational numbers. Well, integers are fine for quite a few things in mathematics, but again, we have a slight problem. Not everything is a whole number that's positive or negative or 0. Okay, we saw that dollars, for example, is like a whole unit. But, for example, with the United States currency, in case you're in a different country, this is one example of the United States currency, we don't just have dollars, we also have a half a dollar or a quarter of a dollar. They're parts, they're smaller parts of a whole, or 5 cents, a penny, a dime. We have different values that are actually smaller than 1 unit. On a number line, 1 unit is exactly, this is from one tick mark to the next tick mark. 1 unit, 2 units, 3 units, and so on. But what if I want to put several points right here from, 0 is fine, and 1 is fine right there, but what if I want to point, let's say there, in the middle, half? Well, we need something that would describe what a half is of something. And that's where rational numbers come in. A rational number is actually defined to be an integer divided by another integer. Well, the divided part can't be 0, technicality. The math symbol is Q, for quotient. Alright? And they're pretty handy to describe a great category of mathematics. Alright? So, in a nutshell, what you want to remember about a rational number, it's an integer, for example, 3 divided by another integer, that's 0. Like 7, for example. Okay? Now, you might say, well, this is a nickel. It's worth 5 cents. Well, 5 cents can be represented with dollars like this, 0.05. So it turns out certain decimal numbers, not all decimals, but certain decimal numbers are also rational numbers. Oh, well, which one? Well, definitely something like this, or let's say 0.25 for a quarter, 0.01, 0.10, 0.5. Now, on paper, I like putting a 0 in front of all these decimals. So you'll see me do that quite a bit. And that's so I don't lose the decimal point. You'd be surprised how many times I write something like, 0.5, and you probably can't even see that. Okay? Or I write down 0.5 so fast it looks like a line. I think, oops, that's a -5. And I make a mistake, and I get it wrong, and life is not good. So I will try to put a 0 in front of my decimals. Now, what about other types of decimals? Okay? Let's talk about that next. Now we can see I've zoomed in a bit on the number line. There's my 0, 1, 2, negatives are in this direction here. But now look what I did. I subdivided each entire unit. So each one being 1, 2, 3. This is 1, that's 2. And I would like to represent this point right here. Well, what is that? Well, it looks like we split this up in 3 parts. So parts of 3, and it looks like it's the 1, 2, second part of 3 sections. Well, sure, most people can recognize that to be 2/3. So fractions can be represented on a number line, and this is how it would look like. Just 2/3, and you put a point there. Now, how can we represent this fraction in decimal form? Well, you put the 3 out there, and the 2's in here. Well, 3 doesn't fit into 2, so 0. So I'm going to tack on a 0 and put a decimal point right there. Here's a decimal point right there. You say, well, how many 3 fits into 20? Well, 6 of those. 6 times, I'm going to do this, by the way, the American way of doing division. There's also European or Latin American way of doing long division. We'll probably say that for another lecture. Anyway, we're going to get 18. We subtract, we're going to get 2. And we tack on a 0 here, a 0 here. And guess what? We're going to keep getting 20, 20, 20, 20, 20. And we're going to keep getting 6, 6, 6, 6, 6, 6, 6 forever. That's interesting. What does that tell us? Well, we know 2/3 is a rational number because it can be represented by an integer divided by an integer, not 0. I can place it on an underline, but its decimal representation doesn't stop like 0.5 or 0.25 where we saw earlier. It never ends. And notice it's always 6, 6, 6, 6. Now, that always has to be the case. It has to be exactly just the same number. Well, no. I can have another number, for example, 0.12120, 1212 forever. Or I can have, let's say, 0.357, 357, 357 forever. Okay? As long as it's a set number of repeating digits along the way, that's actually a rational number. Now, how can we represent these decimals in a more... Obviously, I can't write it forever. So the 0.666 forever can be represented with a bar on the calculator over the 6. And this number over here, I can represent that with a bar over 1, 2. This can be represented by 3, 5, 7, and a bar over the 3 numbers. And that just means the number repeats itself forever. And that, in a nutshell, is what the rational numbers are all about. Here's some examples of these.